Hello, today's topic of discussion is Legendre's polynomial. We have divided this chapter 4 into 5 modules. In module 1, we start with a brief discussion of Legendre's polynomial. Then we move into Legendre's equation and its solutions. In module 2, we derive the generating function of Legendre's polynomial. Module 3 discusses the orthogonal property of Legendre's polynomial along with some examples. In module 4, we derive few recurrence relations along with the proofs. Also, Roderick's formula is also derived. We end this chapter with Legendre's function of second kind, which is done in details in module 5. Let us now move to module 1, slide 1. We start with module 1, a brief introduction. The Legendre's polynomial were first introduced in 1782 by Adrien Marie Legendre as the coefficients in the expansion of Newtonian potential. Let us now see why actually you study this Legendre's polynomial. Legendre's polynomial are special cases of Legendre functions, which are important in problems involving spheres or spherical coordinates. Due to their orthogonality property, they are also useful in numerical analysis. Legendre polynomials are used in fluid dynamics to study the flow around the outside of a puff of hot gas rising through the air. Legendre's polynomial are used to obtain global bounds on the variation of the phase of an elastic scattering amplitude. Legendre polynomials are also used in multipole expansions. The picture which you are seeing is not of the mathematician Legendre. For 2 decades, this picture, which is of a French politician Louis Legendre, was assumed to be the picture of the mathematician Legendre. And for 200 years, we took this politician as our French mathematician A. M. Legendre till 2005, when the mistake was discovered. So, what is the picture, the true picture of Legendre? Unfortunately, we do not have it. This is the only sketch that is available in the internet, which gives you the Legendre's portrait, which was done by the French artist Julien Leopold Boilly. We now look into Legendre's equation and derive its solution. The equation which you see, 1 minus x square y double dash, which is d2y dx square, minus 2x dy dx plus n into n plus 1 into y equal to 0, where n is a positive integer. This equation is called Legendre's equation. We will now obtain a solution of this Legendre's equation. Let the series solution of this Legendre equation be of the form y equal to summation m equal to 0 to infinity C m x to the power k minus m, where C naught not equal to 0. What we do now is we substitute this solution in the Legendre's equation. That means, we find the first derivative dy dx, the second derivative d2y dx square, and put those values in this differential equation. And when you do that, you get an equation in this form: 1 minus x square summation m equal to 0 to infinity C m k minus m minus 1 x to the power k minus m minus 2 minus 2x summation m equal to 0 to infinity C m k minus m k to the power k x to the power k minus m minus 1 plus n into n minus 1 summation m equal to 0 to infinity Cm x to the power k minus m equal to 0. Next we simplify that equation and bring it in this form. What we will do now is to obtain indicial equation from this equation number 4. By indicial equation I mean that you obtain the coefficient of highest power of x from this equation. Now, to obtain the highest power of x from this equation, you need to put a value of m such that it gives the highest power of x. For example, if I put m equal to 0 here, I get x to the power k, and here I get x to the power k minus 2. If I put m equal to 1, I get x to the power k minus 1 here and x to the power k minus 3 here. So, obviously, x to the power k is the highest power of x that we obtain from this equation by substituting m equal to 0. So, the indicial equation in this case will be by putting m equal to 0 in this particular equation, and when we do that you get an equation of the form C0 k minus 0 minus n k minus 0 plus n plus 1, which is this equation number 5. Obviously, C0 is not equal to 0 by assumption. So, you are left with a quadratic equation in k, which you solve and you get the roots of k as k equal to n and minus of n plus 1, which is unequal and differ by an integer. Next, we equate the coefficient of x to the power k minus 1 to 0 in this particular expression, and if you do that, if I substitute m equal to 1, I get the coefficient of x to the power k minus 1. So, by putting m equal to 1. So, I will get by substituting m equal to 1 C1 k minus 1 minus n k minus 1 plus n plus 1 x to the power k minus 1. So, I get an expression like this. Now, already we have solved for k, which gives the value k equal to n and k equal to minus n plus 1. If we substitute that here, we are not getting the value to be 0. So, for k equal to n and for k equal to minus of n plus 1, none of these expressions is 0, which implies our C1 is equal to 0. Next, we equate to 0 the coefficient of x to the power k minus m in this expression. Now, as you can see here, we already have x to the power k minus m. So, the coefficient of x to the power m in this case is going to be k minus m minus n, k minus m plus n plus 1. Now, what will be the coefficient of x to the power k minus m in this particular summation? What you do here is, I will replace this m by m minus 2, and if you do that, please note this is a minus sign here. So, if I replace this m by m minus 2, this becomes k minus m plus 2 and minus 2. So, that 2 and minus 2 plus 2 and minus 2 cancelled, and you are left with x to the power k minus m. When you do that here, you have to do the similar thing here, you have to do the similar thing here, and you have to do the similar thing here. That is, you replace each of these m by m minus 2, and when you do that, you get this coefficient of x to the power k minus m here as c of m minus 2. I replace this by m minus 2. So, k minus m plus 2, similar thing here. So, k minus m plus 1 minus this whole expression, because this is already the coefficient of x to the power k minus m. So, we equate this whole expression to 0, and you are left with Cm equal to k minus m plus 2, k minus m plus 1, k divided by k minus m minus n, k minus m plus n plus 1, Cm minus 2. So, we obtain this recurrence relation of Cm in terms of Cm minus 2. Case 1, When k equal to n, we substitute this value in this particular expression when k equal to n, and when you do that, you get an expression minus of n minus m plus 2, n minus m plus 1 divided by m 2n minus m plus 1 into c m minus 2. Now, in this recurrence relation, you substitute m equal to 3, 5, 7 and so on, all the odd numbers. When you do that, when you substitute m equal to 3, this gives you n minus 3 plus 2, n minus 3 plus 1, m, this is 3, 2n minus 3 plus 1 into c 3 minus 2, which is c 1. And already we have derived that your c 1 is 0. And since c 1 is 0, in this case this whole expression becomes 0 and you get c 3 is equal to 0. If you continue like this, if I put m equal to 5 now, then this becomes c 5, here it is going to be some number, and then c 5 minus 2, which is c 3, and it becomes 0, because already you have calculated that c 3 equal to 0. So, c 3, c 5, c 7, all the odd numbers c 2n plus 1, they are all coming to be 0, since your c 1 is 0. We now look what happens when you put the values of m to be even numbers, that is m equal to 2, 4, 6 in this particular expression. When I put m equal to 2, I get c 2 here, then n minus 2 plus 2, which gives you n, n minus 2 plus 1, which gives you n minus 1, divided by 2 times 2n minus 1, which happens when you put m equal to 2 here, and c m minus 2. So, this becomes c 0. So, you get an expression of c 2 in terms of c 0. Next, you put m equal to 4 in this particular expression, and when you do that, you get c 4 is equal to minus of n minus 2, n minus 3, 4 times 2n minus 3 into c 2. Already you have already calculated the c 2 here. So, substitute this value of c 2 from here in here, and you will get an expression of c 4, which is equal to n into n minus 1 into n minus 2 into n minus 3 divided by 2 into 4 into 2n minus 1 into 2n minus 3 times c 0. Like that, you can calculate c 6, c 8 and so on. Now, you rewrite the equation number 2, which is in this form, y equal to summation m equal to 0 to infinity c m x to the power k minus m, where c 0 not equal to 0 for k equal to n. And if I substitute it here and write it in the expanded form, I will get this to be y equal to c 0 x to the power n plus c 1 x to the power n minus 1 plus c 2 x to the power n minus 2 plus dot dot dot. Now, substituting all the values of c I from this previous expressions, that is all c i's which are started with the odd numbers are 0, and all the even values of c I, that is c 2, c 4, c 6 and so on. If you substitute it here and replace c 0 by an arbitrary constant a, you get an expression like this given in 10, that is y equal to a times x to the power n minus n into n minus 1, 2 into 2n minus 1 x to the power n minus 2 plus n into n minus 1 into n minus 2 into n minus 3 divided by 2 into 4 into 2n minus 1 into 2n minus 3 x to the power n minus 4 minus and so on. Next, we look into case 2, where you substitute k equal to minus of n plus 1. Please note, these are the roots of the initial equation which we have calculated before. And if you put k equal to minus of n plus 1 in this particular expression 7 and simplify, you will get an expression like this. that is Cm equal to n plus 1 minus 1 n plus m divided by m into 2n plus m plus 1 into Cm minus 2. In the similar manner, we now put m equal to 2, 4, 6 in this particular expression. Please note, if you are going to put m equal to 3, 5, 7, all the odd numbers, you are again going to get all the Ci's to be 0 when they are all odd. So, we do not show it in this slide, we just put m equal to 2, 4, 6 in this particular expression. And when you do that, you get C2 to be n plus 1 into n plus 2 divided by 2 times 2n plus 3 into C0. C4 will be n plus 4 n plus 2 into n plus 4 divided by 4 times 2n plus 5 into C2, and when you substitute this C2 here, you are going to get this whole expression. And similarly, you can calculate C6, C8 and so on. Now, for k equal to minus of n plus 1, we look into the infinite series y equal to summation m equal to 0 to infinity Cm x to the power k minus m when C0 not equal to 0. When you expand this, it is going to give an expression like this given in 12, that is y equal to C0 x to the power minus n minus 1 plus C1 x to the power minus n minus 2 plus C2 x to the power minus n minus 3 and so on. Substituting all the values of Ci's that we have calculated previously and replacing C0 by an arbitrary constant b, we get an expression y equal to b times x to the power minus n minus 1 plus n plus 1 into n plus 2 divided by 2 times 2n plus 3 into x to the power minus n minus 3 plus n plus 1 into n plus 2 into n plus 3 into n plus 4 divided by 2 into 4 into 2n plus 3, 2n plus 5, x to the power minus n minus 5 and so on. So, what you see here y1, y2, they are the two solutions of this Legendre's equation, and these two solutions are linearly independent. So, I rename one of the solution as y1 and the other as y2, and these two are the linearly independent solution of the Legendre's equation 1 minus x square d2y dx square minus 2x dy dx plus n into n plus 1 y equal to 0. Now, taking the value of a to be 1, 3, 5 into 2n minus 1 divided by n factorial, the solution y1, they can be expressed in this form, which we denote by Pnx, and this Pnx is called a Legendre's polynomial of degree n or a Legendre's function of first kind. So, thus the expression for this Legendre's polynomial of degree n is given by Pnx equal to 135 dot 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 2n minus 1 divided by n factorial. The whole thing is multiplied by this expression x to the power n minus n into n minus 1 divided by 2 into 2n minus 1 x to the power n minus 2 plus n into n minus 1 into n minus 2 into n minus 3 divided by 2.4 into 2n minus 1 2n minus 3 x to the power n minus 4 minus more terms are there. By taking b equal to n divided by 1.3.5.2n plus 1, the solution y2, which is denoted by Qnx, is called the Legendre's function of second kind, and we have the expression Qnx to be n factorial divided by 1.3.5 into 2n plus 1 into x to the power minus of n plus 1 plus n plus 1 into n plus 2 divided by 2 into 2n plus 3 x to the power minus of n plus 3 plus n plus 1 into n plus 2 into n plus 3 into n plus 4 divided by 2.4 into 2n plus 3 into 2n plus 5 x to the power minus of n plus 5 plus dot dot. Please note, since n is a positive integer, this Qnx is an infinite series and not a polynomial, and that is why we call this as Legendre's function of second kind, not a Legendre's polynomial of second kind. So, with this we wrap up the module 1, where we look into a brief introduction of Legendre's polynomial. Then we look into the solution of Legendre's equation, and we found that we get the first two linearly independent solution. The first one we call the Legendre's polynomial or Legendre's function of first kind, and the second one Qnx we call the Legendre's function of second kind. We have just obtained two linearly independent solutions of the Legendre's equation, namely Pnx and Qnx. The first one is the Legendre's polynomial or Legendre's function of first kind, and the second one the Legendre's function of second kind. We now look into few examples involving Legendre's polynomial or Legendre's function of first kind. We now start with few examples. The first one, let us determine first few Legendre's polynomial. As seen before, the Legendre's polynomial of degree n is defined by this expression. Now we are going to put n equal to 0, 1, 2, 3 and to see how many Legendre's polynomial we can generate. For n equal to 0, if you put this value here, please note all these numbers are odd numbers. So, 0 you cannot put it here. So, 0 you will put it here and you will put it here. That is why in P0x you get x to the power 0 by 0 factorial and the value is 1. For n equal to 1, if I pluck n equal to 1 here, I get 2 minus 1 which is 1. So, it will stop here. Then x to the power 1 divided by 1 factorial, and for n equal to 1 all these terms become 0. So, that is why you get P1x equal to 1 into x to the power 1 by 1 factorial in which is equal to x. When you put n equal to 2, here you get 3. So, this will continue 1 into 3 divided by 2 factorial x square, and you put n equal to 2 here. So, 2 into 2 minus 1 divided by 2 into 2 into this is 4 minus 1 x to the power 2 minus 2 which is 0. So, you get this particular term, that is half 3 x square minus 1, and you can put 3, 4, 5 whatever number you can there, and you can generate the Legendre polynomials here. If I now draw the graph here, this is what you get of the first 5 Legendre polynomial. For P0x, it is just a straight line parallel to the x axis. For P1x, it is equal to x, which is nothing but a straight line passing through the origin, making an angle of 45 degree. For P2x, which is half of 3x square minus 1, it is nothing but a parabola which is given by this blue line here. Likewise, you can solve for, you can plot for P4x and P5x, and you get the corresponding curves. Our next example, given a polynomial 2x cube plus 2x square minus x minus 3, we are going to express this in terms of Legendre's polynomial. So, the first what we do is we calculate what is x cube, x square and x in terms of the Legendre polynomial. Here P0x, as you can see, it is 1, P1x is x, P2x is half of 3x square minus 1, and hence x square will be 2 P2 plus 1 divided by 2. Likewise, P3x is this expression, and we can calculate x cube from this expression. Now, in the given expression, in the given polynomial, we substitute the values of x cube, x square, x and the constant here, and if you simplify, you get the value to be 1 by 15, 12 P3x plus 20 P2x plus 3 P1x minus 45 P0x. So, this is the solution of this particular problem. Example 3, we have to show that P dash n1 equal to half n into n plus 1. Now, P n x is a solution of the Legendre's equation, and hence it is going to satisfy the Legendre's equation. So, we in the Legendre's equation we have replaced the variable y with P n x, and you get this expression 14. Now, you put x equal to 1 in this expression. If you do that, the first term vanishes, and then you put x equal to 1 here, here and here. And using the result that P n 1 is equal to 1, we will get P dash n 1 is equal to half n into n plus 1. Our next example, you have to prove that all the roots of P n x are distinct. That means they are not repeated. So, to prove that, we use the method of contradiction. So, we assume let P n x are not let the roots of P n x are not distinct. That means there must be at least two roots which must be equal, and let be beta. Now, from the theory of equation we get that P n beta is equal to 0 and P n dash beta is equal to 0. Now, since P n x is a solution of the Legendre's equation, we have that 1 minus x square P double dash x minus 2 x P dash n x plus n into n plus 1 P n x is equal to 0. That is, P n x satisfies the Legendre's equation. We now use Leibniz theorem and differentiate this expression r times. If you do that, after a little simplification, you will come across this particular expression. Putting r equal to 0 and x equal to beta, we get this particular expression. The reason is that if you put r equal to 0 here, you get P n dash beta, and here P n double dash beta is equal to 0. If you put r equal to 1 and x equal to beta here, and using the previous expressions, we will get P n double dash beta equal to 0. Similarly, if you put r equal to 3, 4, likewise n minus 2, and if you follow the same procedure, you will arrive to the conclusion that P n beta, the nth derivative, is equal to 0 at the point x equal to beta. Now, we already have the expression for P n x is equal to 1.53.5 into 2 n minus 1 divided by n factorial multiplied by this whole expression. Now, if we differentiate this n number of times, since this is x to the power n, we will be getting this whole constant here multiplied by n factorial. Now, in one case you have seen that this expression is equal to 0 at the point x equal to beta, and in the other case you see that this expression is not equal to 0 at x equal to beta, and these results are contradictory, and this is because we have assumed that the roots are not distinct. Hence, we conclude that all the roots of P n x must be distinct. Summing up module 1, we start by looking into the brief introduction of Legendre's polynomial. We then move on to the solutions of the Legendre's equation. The two solutions are linearly independent, which we denote by P n x and Q n x. P n x, Legendre's polynomial or Legendre's function of first kind, and Q n x, Legendre's function of second kind. In the next module, that is module 2, we will learn about the generating function of the Legendre's polynomial. Thank you.